So, as promised in the last class, we had to do two proofs. One is a proof for strong duality for convex programming problems, another is a slightly different thing. It relates to linear programming problems. So, our main issue was to prove the strong duality for convex programming problem and show that if the Slater condition fails in case of the convex programming problem, then a finite duality gap may arise. So, the duality gap, which is the difference between the minimum value of the primal and the maximum value of the dual, is 0 when Slater condition holds and could be non-zero, could be finitely non-zero if the Slater condition fails. So, let us first consider the problem. Let us just go back to inequality constraints. How you will do it for equality constraints would be homework. So, this is my problem CP, where for our convenience C is consists of all x in Rn which satisfies the following m inequalities, and each of these are convex functions, and this naturally is a convex function. No differentiability assumption has been assumed at all. And you see, now suppose Slater holds, that is, there exists x hat such that g I x hat is strictly less than 0 for every I. My claim is the following: strong duality holds for CP. Now, the issue is issue is that Slater condition must hold, that is, we are assuming that this set C has a non-empty interior. Now, you might ask me the question, what happens if Slater does not hold? Does that mean that my strong duality can fail even for the convex programming case? The answer is yes. We will show by an example that strong duality will fail even if Slater holds and the problem is convex, a very simple looking problem. But what can also happen, that you might observe that the Slater does not hold, but strong duality is still holding. The question is why the Slater is holding, but the strong duality results are not holding. In such a case, you really have to note the following, that if you find that strong duality holds even if even when Slater is not holding, then there is something else which is slightly more general than Slater. Such conditions are holding on the constraints. So, there could be a constraint qualification for a convex programming problem more general than Slater, and that condition holds, that gives rise to the strong duality result. So, Slater condition is not the only condition on which convex programming is dependent. If you have listened to the lecture, you would have observed Slater. So, Slater is not the only condition on which this is dependent, and one can actually go beyond this, but keeping in view the level of the course that we are going to speak about, we are not going to get into those things. That is the area of current research which has started from the maybe just from 99 to and 2000. So, it is quite recent research. So, those who is not satiated by the answer and wants to have more, especially those who are actually in the field of optimization and PhD students in optimization who are listening to this lecture, they could just go to the internet and search for convex problems, convex programming without Slater condition. There is a huge literature on it. Also, if you look at into this book, in which I am also one of the authors, Optimality Conditions in Convex Optimization, a book which I had already mentioned. So, in this book published by Taylor and Francis, written jointly with Professor Anulekha Dhara, this book also contains a lot of material concerning to this fact. So, okay, let us come into our own world where Slater holds, which is a good problem, and most of the standard optimization problems Slater holds, standard convex problems Slater holds. So, now let X star solve CP. Since Slater holds, there exists a lambda bar element of Rm plus such that L x bar lambda is less than L x bar lambda bar is less than L x lambda bar. This is one condition that holds true for every x in Rn and lambda element of Rn plus. Let me just tell you that I do not mention what a Lagrangian is again, because you have already by now seen the term for quite a long time to really immediately know in your mind that this is nothing but f x plus lambda 1 bar lambda 1 g x, lambda 2 g 2 x, lambda 3 g 3 x plus dot 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 dot. Okay. And the second condition, which is called the complementary slackness condition, tells us this, that is both of lambda i's and g I x bar cannot have hold with strict inequality at the same time. Now, what do I have? I have the following. I know that L of x bar lambda bar is actually f of x bar, and which is nothing but the value of the problem CP. So, you see how saddle point condition leads to a strong duality once you know that f of x bar is equal to minimum of L x lambda bar x element of Rn. This is a standard thing that you know from saddle point conditions. This fact means this. So, this condition on the right hand side, this one, leads to this condition. Now, what is by definition? This is nothing but theta times lambda bar. So, what I have is f of x bar is equal to theta times lambda bar. Now, take any lambda greater than equal to 0, that is lambda element of Rn plus, then what would happen is the following. You will immediately know that f of x bar is bigger than equal to theta of lambda by weak duality. See, once you know this fact, then you will immediately see this would imply, taking into view this fact, that theta lambda bar is bigger than equal to theta lambda for all lambda in R m plus. So, what does that show? It shows lambda bar maximizes theta over R m plus just by the definition of a maximum. Okay. So, and so the value of the dual problem is theta lambda bar. So, f x bar, which is value of the primal problem C p, is same as theta lambda bar, which is the value of the dual problem d p, and that is exactly what strong duality means. Now, every convex programming problem need not have a point where its minimum value is achieved, because if I take say e to the power minus x, so if I consider the program and if you draw the graph of this function at 0 it is 1 and then exponentially goes down towards 0, very bad looking map drawing. So, this is the functional value e to the power minus x is f x. Okay. So, now it goes down towards 0 very fast, it asymptotically approaches the x axis, but there is no point on the x axis or the real line where e to the power minus x actually becomes 0. So, the minimum value, so the infimum value of e to the power minus x is 0, but a minimizer does not exist. So, this can be a situation. So, if I have such a problem, then what is my dual problem? So, for example, what happens to my dual problem? For example, in this case, if I look at this problem, my dual problem is there is no g I x. So, now, x element of R, this system of constraints, right. Obviously, there is an x where for which x is strictly less than 0, Slater condition actually holds in that sense. So, in this case, if I write theta lambda, this is unconstrained case. So, can I write a theta lambda? My question. See, in this unconstrained case, if I try to write something like this, and so okay, my Lagrangian is this, there is no g's, so there is no lambdas. Then I cannot define something like a theta lambda because there is no such lambda here. That is why the writing of Lagrangian and the writing of the dual problem only makes sense when you have constraint problem. Okay, you might ask me, okay, you have given an example of an unconstrained problem where there is no, is a convex problem and there is no point where it reaches the minimum. Can you give me an example of a constraint problem where such a thing is happening? Okay, I will give you an example. So, here I have a convex problem which is extended valued, and then this convex problem is actually this, the epigraph is this is your APF, Now, I consider minimum of f x over x element of 0 1. Then of course, you observe the same thing happens, that this function as x becomes larger, the function value rapidly goes towards 0, but it does never reach 0. There is no point x for which 1 by x becomes 0. It rapidly declines to 0, but there is no x for which it goes there. So, what happens here again is inf of f x over not 0 1, sorry, 0 2, maybe for your convenience I will make this r plus. But no minimizer exists. So, here is a constraint case. Of course, I could have taken like this and have a whole thing on the closed set, but okay, does not matter. Let me now go back and ask this question. If we know that C p has a lower bound, but does not have a minimizer, then my question is, what happens to the dual problem? Can we say anything about the dual? So, let us now argue step by step. So, let us see what would be the steps of that argument. The argument is as follows. Now, because this problem has a lower bound, the problem has an infimum. So, let alpha okay, this is what you know. Now, once I know this, the following is true. This system has no solution. Now, if the system has no solution, then what can we further say? So, before we get into any other thing, just again let us reiterate, we assume that Slater condition holds. Now, okay, if this has no solution, by separation arguments or by Gordon's theorem, theorem of the alternative, which we have already walked through. So, by Gordon's theorem of the alternative, we have that there exists lambda naught bigger than equal to 0, lambda 1 bigger than equal to 0, lambda m bigger than equal to 0, such that lambda naught, lambda 1, lambda m collectively this is not 0, and lambda naught and you reach this expression. So, this is what you get, because this above system has no solution and each of these functions are convex, which is very clear because this comes out from the data of the problem. Now, if this I have to put I equal to 1 to m. Now, let us see what we can do. If I put Slater condition, let me see what happens. Now, you see I will assume that lambda naught is 0. Because of Slater condition, I am trying to prove that lambda naught is strictly greater than 0, but we will go by the reductio ad absurdum procedure of mathematics or proof by contradiction or so. So, maybe it is better to write in this way, it is much more simpler to understand. First, let me write what I claim. The claim is that lambda naught is strictly greater than 0, because Slater holds. The interesting part of mathematics is that when you give a lecture and when you do a proof of a thing, you possibly do it so step by step and it appears so structured, people would wonder how did one get into one's mind such a structure, how could one figure out that this would be the structure of a proof. But no, let me assert you that all these were done earlier using guess and test and getting ideas from numerical examples. Later on the things were more formalized and unified and put into a form which can be readily accessible by many people, and that is why you would see that most mathematics proofs are highly structured, unless some it is a issue of research proof or proof of a completely new thing been given, where there can be lot of hand wavings and lot of things which are not very clear. But so when we are talking about standard things in mathematics, you will see the proof is very structured, very well written, because it is not because somebody suddenly came and one day started writing all those, but because a lot of people's idea have gone into refining the idea in proving the theorem. So, there is a very famous statement by a mathematician called Giancarlo Rota of MIT, who speaks about F. Rees. Rees representation theorem is absolutely fundamental to functional analysis, and that is by Rees representation theorem we can show that every linear map on Rn is nothing but the inner product, the dot product, which is very important thing. So, when Rees used to write a paper, he never wrote it down immediately. He wrote a paper, published in Oxford journal, then kept on refining it with the new ideas been pushed in and published in some still better journal, while he kept on meditating on it, and then at a much later stage he would publish a final version of what he wanted. So, this is the thing that a person like F. Rees used to do. So, a refinement of a theorem comes after many steps. So, what you see is a very defined version. You might think that I am just giving step by step as if by magic I have come to know the rules. No, these are all by guess and test, and then it has been refined and written in this form. So, now my claim is lambda naught is strictly bigger than 0. If not, then lambda naught is 0, and this would imply that this expression is now greater than or equal to 0, this expression vanishing because you put lambda not equal to 0. Now, this expression holds for all x, because this expression had been true for all x. Now, in particular it is true for the x hat for which every I at every I g I x hat is satisfied with a strict inequality. Thus, for x equal to x hat, it would imply that summation I equal to 1 to m this is what we have from the other equation just we had in the last page, this one. Now, since x hat, since Slater holds, sorry not x hat, since Slater holds, we have if I write down this expression would be this expression would look like this, but now look at this expression, forget this one. Now, for each of these are strictly less than 0. Lambda 1 to lambda m all are bigger than equal to 0, but since lambda naught is always has been assumed to be 0, then the whole, and we know that the whole vector lambda naught, lambda 1, lambda 2, lambda m is not 0. So, among these lambda 1, lambda 2, lambda m, one non-zero quantity is there because of the fact that we have chosen lambda naught equal to 0. So, this would imply that summation means this expression, because these are all, because there is one element of them positive, say lambda 1 is positive. So, this will become a strictly negative quantity. So, finally, this, so what you have finally is this expression, right. But I also have this expression from the other one. So, putting x equal to x hat, because this is true for all x, putting x equal to x hat in particular, by choosing the particular x hat which for which Slater is holding, I will get this, but actually what I should get is this. So, there is a contradiction. So, this implies, so thus lambda naught is not equal to 0, and so we have f of x minus alpha plus summation lambda I by lambda naught So, I divide both sides by lambda naught because lambda naught is positive. So, set lambda I bar is equal to lambda I by lambda naught. Okay. So, this implies now f of x plus summation I equal to 1 to m lambda I bar alpha, which is the infimum or which is the value of p. This is also the value of p, the infimum or the minimum value of the problem Cp, sorry not p, Cp. Now, what is this? If you look at it very carefully, what is this? What is this expression? It is nothing but L x lambda bar, and that is greater than equal to alpha, which is the value of Cp. Okay. See, for the original problem I just know that it has a lower bound, I do not know whether there is a minimizer for which the lower bound is attained or the infimum is attained. So, let me rewrite L x of lambda bar is bigger than alpha is equal to val of Cp. So, now if I take the infimum over all x in Rn of this expression, sorry, x lambda bar, this becomes bigger than alpha equal to value of Cp, and this is nothing but by the very definition theta lambda bar is greater than equal to value of Cp. But by weak duality, for any lambda element of R m plus, theta of lambda bar is bigger than value of Cp is bigger than value of theta of lambda. But again by weak duality, because now value of Cp is actually bigger than theta. No, so this would imply from here that theta lambda bar is greater than equal to theta lambda. So, you have a lambda bar which maximizes theta. So, you know the dual upper bound exists, the dual maximizer exists, there is a lambda bar for which the dual function is maximized. But you also have here that by weak duality this is holding, value of Cp is greater than theta times theta of lambda bar. But we have proved that value of Cp is obviously less than theta lambda bar. So, combining this I have value of Cp is equal to theta lambda bar. So, what is theta lambda bar? It is nothing but value of dP. So, interesting part is that even if the original problem does not have a lower bound, say I am making a mistake, I track back. Even if the original problem does not have a minimizer, it can have a lower bound, it has a lower bound, that is what we have assumed, but it does not have a minimizer. There is no x for which that infimum value is achieved, that alpha value is achieved, there is no x such that f x bar is alpha. Then it does not matter if the dual problem is feasible, it is all right. If the dual problem is feasible, which it is, because dual problem is always feasible here, because lambda is greater than or equal to 0, lambda is in R m plus, which is all right. So, then the strong duality not only holds under stator condition, but the dual maximum value is achieved, that there is a lambda bar for which the dual value is achieved. Now, we are going to give an example what would happen even in the case of convex programming when Slater fails. So, what happens when Slater fails? So, let me write down, this is what this example is famous in optimization literature as Duffin's duality gap. Here is a problem, original problem P or Cp is to find the infimum over x1 x2, both x1 x2 is in R. So, this is in R2, find this subject to root over x1 square plus x2 square is less than x1. Now, let me figure out what is the feasible set of this problem. It is only telling that x1 square, whatever I take for x1, if I take x2 to be 0, then my feasibility is guaranteed. So, what it would happen? It will immediately tell me that whatever x1 I take, I will have x1 square plus x2 square is less than x1 square. So, I will have x2 square is equal to is less than equal to 0, but x2 square is equal to 0 then, because x2 square is always greater than equal to 0. So, I will get x2 equal to 0. So, my feasible set consists elements of this form. This feasible set is a subset of, in fact, a proper subset of R2. So, this is a proper constraint optimization problem, and you have to observe that Slater does not hold. Slater condition does not hold. That is, if I put 0 here and if I take any x1, it will become x1 equal to x1. So, there will be no Slater condition holding. There is no strict inequalities are never strict. At all points this inequality is active. Now, so x2 is 0. So, inf of in C now is nothing but E x2 is 0 is 1, and that is the value of P. So, what about the dual problem? Dual problem is max of theta lambda, lambda element of, in this case I have one constant. So, it is in R plus, right. So, here m is actually 1. Now, this will be something very simple. Observe that I can write theta lambda as inf of x in R2. I am constructing the Lagrangian L. This minus this is less than equal to 0. So, this is my theta lambda. Now, how do I compute that theta lambda? How do I know what is theta lambda? We will show that theta lambda is 0 for whatever lambda we take, and so the maximum value would be 0, and there is a duality gap. Slater does not hold. Let us see how do I compute this. The interesting part is that you see what would happen if I fix up the x2. So, this is x1 and this is my x2. If I fix up my x2 and then I vary my x1, so these are the points I will walk through. Then as x1 becomes larger and larger, right. So, as if x2 is fixed and x1 I ran them to plus infinity, then does not matter even if it goes to. So, what would happen if I ran this to plus infinity, then the difference between these two keeps on shrinking. So, then x1 square, because x2 is fixed, because finally the infinity, the larger number will dominate, this is going to 0. So, on this line means once x2 is fixed, then the minimum value over x1 is nothing but x2. So, infimum for a fixed x2, for each x2, infimum x over R2. So, once I fix the x2, I can only move along the line which is passing through x2, which is parallel to x1 axis. So, basically infimum over x1, which is same as infimum over x1, infimum over x element of R2 is same as infimum over x1, x2 plus lambda root x1 square plus x2 square minus x1, this thing is nothing but e to the power x2. So, I know the minimum value of the function over this line when x2 is held fixed, but if I change the x2, again I will know in the same way the minimum value, which will be e x2 of that particular value of x2. So, on each of the lines, the function value, the minimum value of the function when minimized over x1 is just e to the power x2. Now, if I vary the x2, then I am varying the function over the whole plane, and thus I get the minimum over the whole plane, and e to the power x2 you know goes to 0, the minimum is 0. So, theta of lambda is actually 0 for any lambda you choose, any lambda greater than equal to 0 you choose. This implies that value of dp is, this is a 0 function. So, value of Cp minus value of Tp is 1, and which is a positive duality gap. So, even for a convex problem, in the case of non-satisfaction of Slater condition, duality gap may arise. So, there is when the general conditions that might satisfy that, which is something at the level of research, which we had just spoken of, that might not even hold for this particular case, in fact does not hold for this particular case. So, with this interesting example I stop here today, and from the next class onwards we start a fascinating journey into what I call the pleasures of linear programming. And after I finish this pleasures of linear programming, my next set of lectures would be, I would like to call it the joy of semi-definite programming. You see how much fun we will have here. So much things can be said. A lot of difficult problems can be played along with this, with semi-definite programming. So, this will be our theme for quite some time now after this. So, you already have quite a wide idea about the theory of convex programming, and now we are going into very particular type of convex program, and these are the two most important classes of convex programs. So, with this I end today's lecture. Thank you very much and hope to see you tomorrow.